Okay, let's begin. So we are looking at predicate logic. We have looked at the definition of structures. I have just written that definition down on the screen so that you remember that you start with a non-empty universe, and for each symbol in your predicate language you have some appropriate data, as in a subset of appropriate arity, a function of appropriate arity for a relation symbol and function symbol, and a specific element for a constant symbol. Okay. So this is the data, and what we are going to do now is look at some substructures. So you know that, for example, a linear order is a structure in which language? A language consisting of just one binary relation symbol. Then a group is a structure, yeah, in an appropriate language. Then a vector space is a structure in an appropriate language, correct? All of these are structures, and associated with that you always have a suborder, a subgroup, a subspace. Yeah, so they all fall under the same category. So I just thought I will show you how that happens. So given two L structures M and N, well, when I write this, I think you understand. When I write dot dot dot, what does that mean? All this extra data. Yeah, I just write down the name of the symbol for the universe, but I don't write other things. Say that N is a substructure of M written, N is a substructure of M, if, can you tell me something, what should we do with relation symbols? Yes. So if for all, if first of all N should be a subset of M. Yeah, it's a substructure, so it should be a subset to begin with. Then second thing, for each relation symbol, R of arity M. What can I say about Rn? So which tuples are in the relation, the interpretation of the relation in N? They are precisely, I mean, this is an induced relation. So it should be, you interpret it in Rm, and then you only take those tuples which lie in n to the power m. Okay. Then next thing, for each function symbol f of arity n, what should happen? What should be Fn? Fn is precisely the function Fm restricted to n to the power n. Yeah, I mean restricted and co-restricted. So, okay, and for each constant symbol, what should I write? If you talk about a subspace of a vector space, yeah, what happens to the zero? The zero of the bigger space should lie inside the zero of the, should lie inside the smaller space, right? So same thing we are going to write. For each constant symbol C, Cm belongs to n and Cn is equal to Cm. Okay, the constant symbol in the larger structure should be interpreted as an element of the smaller structure, and the interpretation should agree. Okay, any questions about this? So, now tell me, so for example, given M and N L-set structures, L-set structures, N is a substructure of M if and only if what will happen? Correct. N is a subset of M because there is no relation symbol, no function symbol, no constant symbol. Okay, so that was example number 1. Now, given L-ORed structures, M equal to M comma Rm and N equal to N comma Rn. N is a substructure of M if and only if N is a subset of M and Rn is equal to Rm intersection N square. It is a binary relation symbol, N square. So, in case of posets, what we are talking about, I mean suppose this M and N are posets. So, for example, yeah, I mean in particular I am going to use a different color now. If I tell you that this is my A, B, C. Yeah, so it is a 3-element linear order. Then is this, if this is my N and this is my M, yeah, this is an anti-chain. Is this a substructure? No. So what we need is that it should be an induced substructure, correct? So this is not a substructure. Because what happens? A and B are not related here, but they are related here. So do you remember a term like this inclusion has to be what? This is a monotone map. The inclusion is monotone map, but what do we need it? Order embedding. It should also reflect order, right? So that is the property. So in particular for posets, N and M, N is a subset of M if and only if, N is a subset of M and the inclusion map from N to M is an order embedding. Okay, so we are not talking about other subsets. I mean, this is an arbitrary subset where the inclusion is order preserving but not order reflecting. Okay, fine. So let us go to the third one. Now, given LGR structures, do you remember what is LGR? I should give you M, then what should I give you? F from M square to M, and G is a unary function symbol for inverse. So Fm, Gm from M to M, and then Em in M, and you write down n's similarly. Okay, then we say that n is a subset of M if and only if, I mean, I'm not going to write it, but if there are groups that are, if I say that these are groups, yeah, then n is subset of M if and only if n is a subgroup of M. So, for example, integers are a subgroup of rational numbers as an abelian group, right? Because sum of two integers. So, what does this condition say? Yeah, this Fn is restriction of Fm. It says that this subset n is closed under the action of Fm. You have heard the word closed? Yeah, when you talk about a subspace of a vector space, then you say it is closed under the induced scalar multiplication and induced addition. So, everything is about induced. So, I am trying to give you a feel how logic brings everything together under one umbrella, right. So, n is a subgroup. Here it was an order embedding, I mean it was a strong induced subposet. Yeah, maybe I should write it. Yeah, so this is called induced subposet. Okay. So, here it is subgroup, for vector spaces it will be subspace. So, everything whenever you have a prefix sub, yeah, more or less it can be expressed in some logic, not necessarily finite, but it can be expressed. Finitary logic is not necessary. Okay, I am not giving you any more examples, but here we talked about something, yeah. I from n to m is an order embedding. Well, whenever we talk about structures, at the same time we should talk about the morphisms which preserve structures. So, we have seen Boolean algebras, Boolean algebra homomorphism, lattice homomorphism, poset like order preserving maps, right. So, all of those things we should talk about. So, given L structures M and N, a morphism alpha from M to N is a function f from the universe of M to the universe of N, curly N, satisfying the following data. First one, yeah, I mean it is a function, first of all, that I have said. So, for each relation symbol, what should happen? For each relation symbol, R of arity M, can you tell me what will happen? What should alpha do? Oh, sorry, it is a function alpha, not, I should not be using f, yeah, f is reserved for a function symbol. So, right now we are using a different symbol. For each relation symbol R of arity M, I mean relation symbol, think about order relation. If x is less than, if a is less equal b, then you say that alpha a is less equal alpha b. Yeah, so we should talk about that. And a bar in M, right? We have A bar belongs to Rm implies, sorry, maybe I should not use this notation because I am prohibiting you from doing so. So, if A bar belongs to Rm, then so alpha of A1, alpha of A2 up to alpha of Am, this is what we will call alpha of A bar belongs to Rm. Yeah, alpha A bar is the shortcut to write this. Component wise, apply alpha. Any question? Second condition, for each function symbol, f of arity n and A bar in M. Now A bar is a tuple of length little n. What will we have? Well, we can first say Fm applied on A1, A2, An, that we can do, and then we can say, okay, this is a single element of M, I can apply alpha on it, but this is same as, well, I will first apply alpha on each individual pair, and now this is a tuple in N, so I can apply Fn. So this should happen. Now if you think about it, vector space addition, yeah, vector space addition, and you talk about a linear map. What does a linear map do? Well, it takes addition and it maps it to addition of the images. The image of addition, image of sum is sum of images. That's what we are writing here. It's just a more fancy way because we are talking about arbitrary n array function symbols. And finally, what should happen for constant symbols? For each constant symbol, C, we have alpha of C M is equal to Cn. I mean, you also require that a vector space 0, yeah, is preserved by the linear map. Yeah, 0 maps to 0. Well, that's what we are saying here, right? So now let us try to do some examples. In L set, what is a morphism? Oh wait, I should say homomorphism, yeah, L structure homomorphism, or oh, maybe I should do one more thing. Yes. So what is an isomorphism as well? I can write it down in the same definition. Can you tell me what should be the isomorphism? Bijective, yes. It should be a bijective function. Then for each relation symbol R of arity M and A bar in M, what should happen?
Alpha inverse should satisfy the opposite.
Or we just say this is if and only if. It's not if then, it's if and only if, both ways. And then the rest don't matter. They are going to remain same. Okay, only here we needed to make a change. So a bijective map which has if and only if in the relation symbol condition. Okay. So now let me give you an example. L set structure homomorphism. I am going to write HM for homomorphism is what? What should it be? L set structure homomorphism. It's just a function. Yeah, is a function. So functions also we are generalizing, right? Functions are also homomorphisms. There is no structure, but that doesn't mean it doesn't preserve structure. Yeah, it preserves no structure, so it is a homomorphism. Okay. Then L odd structure homomorphism between posets is a monotone map. Okay. Then what about this? Yeah, I am going to give you one interesting example. So let me call it this. It should contain one binary function symbol and one constant. So L is equal to F binary and C unary. Yeah. Then from natural numbers comma plus and 0, I can send it to natural numbers comma multiplication comma 1. What should be the map? Can you think of any? If I do n mapping to 2 to the power n, you understand? So n mapping to 2 to the power n, this is exponential map, yeah, I mean 2 to the power n, and can you tell me what it is? So 2 to the power n1 plus n2 maps to, it is 2 to the power n1 times 2 to the power n2, so the structure is preserved, and also 0 maps to 1. So this is an injective homomorphism. And what about this now? R plus 0 to R plus comma dot comma 1. If I write down the exponential map, e to the power x. This is an isomorphism. Yeah, E is an isomorphism. Yes, I tried to give you one non-trivial example of an isomorphism. Exponential is always an isomorphism from the set of real numbers to set of positive real numbers. Any questions here? So you understand homomorphism, substructures. So lot of algebra, algebra is a general term, okay? Algebra doesn't always refer to the things that you study in algebra course. Yeah, in algebra course you study vector spaces, then groups, rings, fields. Not only those things are algebraic structures. Even relations are algebraic structure. So anything that is finitary in nature, any symbol that is finitary, that is algebra in a general sense. There is also a branch of mathematics called universal algebra, which studies all these things. So a homomorphism is when we are talking about structure preserving maps. And these are all algebraic structures. Yeah, there is nothing infinitary happening here. Even orders are algebraic. Lattice homomorphisms, they will also be homomorphisms in this sense. Yeah. Then Boolean algebras, everything that we have done so far that is encompassed under this notion, that comes together under one umbrella. Yeah, except for, I mean, you haven't studied topological spaces yet, but topological spaces do not fit into this because of the condition that arbitrary union of open sets is open is a clause that is not finitary, and it is about subsets. Yeah, so we cannot quantify over subsets, so it's a strictly higher order structure. Yeah, it's not a first order structure. Any questions? Okay. So then we can start with something new now. I am going to write down a theorem, and I am not going to do a proof, but I will give it to you as an exercise. This is again a proof like substitution theorem, where the proof is really long, but it is straightforward. If you know exactly what you are supposed to do, then you will do it. Okay, so this is called dependency theorem. Okay, suppose L is a language, M is an L structure, phi x bar is a formula, and A bar and B bar are in M. Okay, so you are given this much data. If AI is equal to BI for all xi belonging to the set of free variables of phi. You remember the set of free variables? Yeah, the variables which are not bound. Normally, I mean, we can say that x square plus y square minus 1 equal to 0 is a polynomial equation in x, y, z, but z doesn't appear, right? So therefore, we can have much more larger context than the set of free variables itself. So if AI is equal to BI for all xi in the set of free variables, then M satisfies phi at A bar if and only if M satisfies phi at B bar. Looks obvious? Yeah, but the proof is long. What is the method of proof? Induction on the complexity. Yeah, you just have to go through it. Yeah, I can write it down, but it is just unnecessary, I feel. You can learn more interesting mathematics instead of doing this in the class. Okay, so what we are saying is that the truth of the formula doesn't really depend on the variables which are not free in your formula. Okay, x square plus y square minus 1 is equal to 0. The truth of that formula will not depend on value of z. If I give you 1, 2, 3 and 1, 2, 4, then 3 and 4, those elements don't matter. This is simple. Yeah, how do you do it? By using induction. Do you need to prove anything for terms first? Anything that is about formulas, yeah, you have to prove a similar statement for terms. Can you tell me a similar statement for terms? if T is a term in context x bar and A bar and B bar are arbitrary tuples such that AI is equal to BI for all xi belonging to the variables which occur in T, then the value of the term at A bar is going to be same as the value of the term at B bar. So, there is equality, and equality in the case of terms is replaced by if and only if condition in the case of formulas. Okay, so you have to prove that first and then you have to come here and prove this. Okay. Now, okay, I am going to write down a bunch of definitions. They are not new for you. Yeah. So, suppose gamma of x bar subset of FL is a set of formulas in context x bar. So, this gamma of x bar could be infinite. The only condition that we need is that the number of variables which could occur in that infinite collection of formulas is still finite. That is again from x bar. Yeah, so let us say I am talking about infinitely many polynomials at the same time, but they are all polynomials in x and y. Yeah, so this finiteness is important. Gamma itself could be infinite. Okay. So, say that gamma is satisfiable if, tell me when should it be satisfiable? If there exists a valuation. What is a valuation? Did we define a valuation? I mean, indirectly we did, yes. There exists some A bar belonging to M, and where is M coming from? If there exists, yeah, if there is an L structure M and A bar in M such that M satisfies phi x bar for each phi x bar in gamma x bar. So, each formula in that collection is satisfied by some tuple in some structure. You understand this? So, this definition, I mean right now you are not really worried about knowing what is the actual meaning of satisfiability, right? You know that from propositional logic, which was the baby version of this, we said, oh, there is a valuation which makes every formula true. Now here the truth is dependent. The valuation that somebody talked about earlier, the valuation is this pair M and A bar. Right? If there is a valuation M and A bar which satisfies phi. For each phi. Yeah, I mean there also we did the same thing. We said that capital S is satisfiable if there is a valuation which makes every little s from capital S true. So here also there is for each thing, and the valuation is a structure comma a tuple. Okay. Yes? We need that A bar because we cannot talk about truth. Can you say that phi is true in M? You can't, right?
So we need L structure and some tuple for which.
Yes, and some tuple which makes it true. Yeah, otherwise we can't say that. If I am given this formula x less than y.
No, I think he's right. Like, why did we write M models phi of A bar?
Oh, phi of A bar, sorry, not x bar. Sorry, phi at, yeah. Phi is satisfiable in M at A bar.
That A bar, that fixed A bar should be for all the polynomials or for all.
For all the formulas, there should be a common A bar. Yeah, it's not like for individual formula we choose a different A bar. Yeah, this A bar doesn't depend on phi. Yeah, that's the most important thing. Any questions? So for example, if I give you the set of polynomials in one variable over integers with constant term 0, is it satisfiable? The set of polynomials in Zx with constant term 0, is it satisfiable or not?
Yes. Those are terms, how can they be satisfied?
Oh, I mean polynomial equations, sorry. Maybe I should say px bar equal to 0 with constant term 0. Is it satisfiable?
Yes.
Why?
0.
0 satisfies it, correct. You understand? I mean, I'm not making sense here. I haven't written the language, I haven't written the polynomials properly, but you get the sense. Yeah? I'm not writing polynomials as bracket, bracket, bracket and things. Yeah? I should do that, but this is satisfiable. You understand? Because 0 satisfies it, right? So, when do you say that it is unsatisfiable or
No structure.
right? So, unsatisfiable, I think you can make sense of it. If, I mean negation of this, yeah? What is it? There is a quantifier over here. So, there is a quantifier. If there exists an L structure, so the negation would be for all L structures. The inside part doesn't happen. Yeah, for all L structures M and for all A bar in M, there is a formula. Yeah, this for all is also negated. There is a formula phi in gamma such that phi is not true in M at A bar. You understand? Do you want me to write it down? Okay. Fine, I will write it down. So say that gamma of x bar is unsatisfiable if it is not satisfiable, i.e. for each L structure M and A bar in M, there is some phi x bar in gamma x bar such that M does not satisfy phi at A bar. You give me one formula, I will give you another thing. Yeah, so for example, yeah, What about this? X equal to 0 and x plus 1 is equal to 0. Is it unsatisfiable?
No. 1 equal to 0.
If 1 is equal to 0, then it is not unsatisfiable. Right? So, I mean, unsatisfiability is a very strong condition. Yeah, it's still satisfiable. Is satisfiable in a structure where in a structure M where 1M is equal to 0M. Right? So, but something like this. Negation x equal to x. Is this satisfiable or unsatisfiable? Yeah, unsatisfiable. It can never be true. For every tuple for every a, little a, in any structure M, you will always have a equal to a. So this is an obviously unsatisfiable. So see, you have to be creative. Yeah, satisfiability is not an easy condition to verify. If 1 and 0 are the same, you have to think about all possibilities at the same time. Any questions?
So that 1 equals 0, does it mean that 1 is interpreted in some structure as 0?
1 and 0 right now, they are just symbols. Yeah, so 1 and 0 can be interpreted as any elements. If they are interpreted as the same element, then obviously this won't happen. Okay, any other questions? All right. Now, there is one more definition missing. Satisfiable, unsatisfiable, and there is always satisfiable. What is that? Tautology. So let's define that now. Is tautologous if, can you tell me what the definition should be? For all L structures, yes. For all L structures M, and for all A bar in M, what should happen? M satisfies phi at A bar for all phi x bar in gamma x bar. Okay, one simple example is what I already gave you. Just do its negation. X equal to x is tautologous. Yeah, this is okay? Good. So, now these conditions actually become a bit easier when you are not talking about formulas but just sentences. You understand sentences? Sentences are formulas without free variables. So, what will this read like? A set of sentences gamma is satisfiable if if there is an M structure, L structure M, such that phi is true in M for all phi in gamma. You understand? So for sentences it's easy because sentences are either true or false without having to worry about what the assignment is. Okay. Now, based on this idea, we are going to define something very interesting. And perhaps this is not a surprise to you. Say that gamma subset of SL is a theory if gamma is satisfiable. Is this a surprise? No. Okay. Then, if gamma is a theory and M satisfies gamma, M satisfies gamma means what? M satisfies phi for each phi in gamma, i.e. M satisfies phi for each phi in gamma, then we say that M is a model of the theory gamma, not the theory, of theory gamma. Yeah, this is where the origin of the word model theory comes from. Model theory is a branch of mathematics, mathematical logic, which studies these things. So we don't worry too much about syntax. Syntax is always there to help us, but we only care about this satisfaction relation. Yeah, that is model theory. So now we are going to write down various examples of theories. Okay. So first example. In L-ORD, yeah, suppose gamma is empty. Is empty set satisfiable? Yes or no? Please raise your hands if you think yes. Only 3 people, and the rest of you are thinking it's not satisfiable. See, what is the meaning of satisfiable? Please check. There is a condition for each formula, but there is no formula. So it's always true at everything. Yeah, in every structure it is true, empty set. Okay, then a model of such a theory is called a directed graph. Any arbitrary L-ORD structure is simply a directed graph. Okay, what is a graph? Directed graph, yeah? A graph is simply a set with a binary relation. That binary relation, if A comma B belongs to R, then you draw an arrow from A to B. So that's how it becomes a directed graph. So for example, example within an example. Okay. So suppose M is equal to 1, 2, 3, comma, now I have to give you a set of 2 element subsets. And Rm equal to, well, I will say 1, 2, then 1, 1, and then 3, 1, 2, 1, and 3, 1. And then I will close this.
So those should be ordered.
Yes, okay, thank you. I should always write this. And then there should not be a last parenthesis, right? Okay. Then how do we present it? Then we draw this digraph. Directed graph is also known as a digraph, yeah. This digraph as, well, I have 1, 2 and 3. Then I will have an arrow from 1 to 2, then I will have an arrow from 2 to 1, I will have an arrow from 3 to 1, and I have a loop from 1 to 1. So this is a directed graph. There are no conditions at all. Okay. Any questions? Now, if I include, yeah, I mean we are looking at the same language. So if gamma is the set of sentences, set of 3 sentences expressing, I am not going to write it again, okay, reflexivity, transitivity and symmetricity, then a model of gamma is what? A set with an equivalence relation. Is M equal to M comma E, where E is an equivalence relation on M. So this gamma is, I can write it as gamma EQREL. Yeah, so this is the theory of equivalence relations. Is it satisfiable? Where? In every equivalence relation. Yeah, in every structure that is an equivalence relation, this is satisfiable. Okay, maybe I should write this. Suppose gamma is equal to, so here I can write maybe gamma digraphs. Yeah, so this is the theory of directed graphs. We studied simple graphs, yeah, while studying application of compactness theorem. What are simple graphs? Irreflexive and symmetric, yes. So if gamma, so simple graph is the set of sentences expressing irreflexivity and symmetricity, then, I mean, first of all, it is satisfiable. Yeah, you know why it is satisfiable, because there are simple graphs. A model of gamma simp graph is a simple graph. G equal to V comma E. Okay, the next example I am going to say something out loud which is weird to hear. So group theory is the collection of the 3 sentences, one which expresses associativity, then identity and inverse. So a group is a model of the group theory of groups. Okay, the word group did not come first. The theory of groups comes first, and then we say a group is a model of the theory of groups. Right? I mean, I should also write perhaps here, if I tell you gamma poset, can you write down what are the sentences? Yeah, reflexivity, transitivity, and antisymmetry. And the model for that would be opposite. Yeah, this is a model. Then, so this is in language L odd. Perhaps I should make a table. I did not think of that. If I write down LGR and the language of groups, which is, oh, perhaps maybe I should, this is 2. Language of groups, I should write down F, G and E. This is 0, this is 1, this is 2. And I should express the sentences, associativity. Yeah, so this is gamma group is associativity. Then identity and inverse. Then what is the model on this side? So this is the these are the sentences. This is the notation of theory, and this is the language. I'm doing a really bad job of writing. Okay, so the model is called a group. Perhaps for everybody's convenience, I should write down one of the axioms. Yeah, so for example, I will write the inverse axiom. For all W1, there is, no, I don't need to say there is. Yeah, I should just say for all W1, the sum of W1 and G of W1 is equal to E, and the sum of G of W1 and W1 is equal to E, and this is complete. So I just want to remind you that whenever you are writing down these sentences, you should always use the variables W, because they are bound variables. Okay, then, well, you can write down the axioms for the theory of vector spaces. Yeah, L R vect. What does it consist of? One binary, then one unary, and one symbol which is scalar multiplication for each element in here. Then you write down the theory of vector spaces, gamma R vect. This is the theory of vector spaces. It talks about associativity, identity. Oh, I should also add one G, yeah, which is for inverse. Associativity, identity, then inverse. Then what else should you require? Commutativity, yes. Then you should also require a bunch of other statements. Yeah, for example, if I say MR of MS of W, yeah, for all W, MR of MS of W is MR plus S of W. Yeah, some conditions like this should also be included. These are, I mean, by the way, the elements, I did not write that, but I will, yeah?
It's MR into S.
Just a moment. Yes, MR into S. MR into S, and then we also have the corresponding things for addition. Yeah, you have more conditions here, around 10 of them. Then scalar multiplication distributes over addition. Yeah, you should also be able to express all those things, and then the model, corresponding model, is called an R vector space. Let me go back a bit when I was defining a theory. Yeah, so the sentences, so this is perhaps in red, sentences in a theory are called axioms of gamma. Yeah, that's where the word axiom also comes into picture. A theory consists of axioms. So the axiom for associativity, axiom for reflexivity, yeah, that is how we have learnt it. Any questions so far? Everything is clear? Okay. Then we can also express in appropriate languages. I am not going to write down too many names now. Yeah, and there are more axioms here also. But if I start using languages like this, like both of them are binary symbols, and then there is C and E, which are zeroary symbols. If this is my language, then I can write down the theory of lattices, yeah, bound lattices. Yeah, so I can say bound lattice. What will I write for bound lattice? Do you remember? Lattice means both operations are, both gamma and both meet and join are associative, commutative, then idempotent, then there is absorption laws, yes, absorption laws, then C is minimum, yes, so C is minimum, E is maximum. How do you express something is minimum? For all W, C is like C meet W is equal to C. Very good. So you know what to do now. Yeah, so finally the model is called a bounded lattice. And you can express in similar ways by adding more symbols if necessary or removing symbols if necessary. Semilattices, bounded semilattices, then distributive lattices, modular lattices, Boolean algebras. Yeah, wherever you have bunch of axioms, they are all theories in appropriate languages. Right? So if I ask you to write down theory of a particular structure, you should be able to do that. Yeah, it's easy. Okay, so given a set gamma x bar, subset of FL, and a formula psi x bar in FL, say that psi x bar is a logical consequence of gamma x bar if, yeah, we have seen written gamma x bar models psi x bar if, I mean, can you recall the definition from propositional logic? T is a logical consequence of capital S if whenever V models S, then V models T. Now we are going to do exactly the same thing. What is the meaning of a model here? there is a structure and a tuple. Okay, if whenever M is an L structure and A bar is in M such that M satisfies gamma at A bar, then M satisfies psi at A bar. You understand M satisfies gamma at A bar? It means M satisfies phi at A bar for each phi in gamma. Same definition, yeah, we haven't changed anything. And for sentences, again this is simpler, yeah. So in particular, if gamma is a subset of SL and psi belongs to SL, say that psi is a logical consequence of gamma if whenever M is an L structure and M models gamma. So M is a model of the theory gamma, then M satisfies psi. But see, in this definition, I never said that gamma has to be satisfiable. If gamma is unsatisfiable, then gamma will always logically imply psi. Yeah, because again the same idea, yeah, that it will generate the entire filter. Okay, I use the word filter. So for filter there should be a Boolean algebra somewhere. Where is the Boolean algebra here? What should we do here? We should define the notion of logical equivalence. Yes. So let us do that while we are here. So, yeah. Say that formulas phi x bar and psi x bar are logically equivalent if whenever M is an L structure and A bar is a tuple in M, then M satisfies phi at A bar. What should I write? If and only if M satisfies psi at A bar. Okay, so simple enough definition. Then when you take logical equivalence classes of formulas, then you will get a Boolean algebra because of F2. Just F2 alone is sufficient for that. Yeah, we will talk more about it in the next lecture, but let me come back to theories. Yeah, so say that a theory gamma is a complete theory if for each psi in SL either psi is a logical consequence of gamma or negation psi is a logical consequence of gamma. Tell me whether both of them can simultaneously happen. Yeah? Can you prove that? Then it won't be satisfiable, yeah? So suppose, so we know that it is a theory. Theory means it is satisfiable. So let M be a model of gamma. If both of them happen, then M models psi and M models negation psi. Well, that's a contradiction. So therefore both of them cannot happen. But in an incomplete theory, what can happen? That there is some gamma, there is some psi, such that gamma doesn't entail psi and gamma doesn't entail negation psi. Yeah? So complete theory essentially makes decisions for everything. For every sentence it makes a decision. And what condition does this remind you of? Psi and negation psi? Ultra filters. Correct. So these are precisely ultra filters. And I need to give you one example of this. Obviously, if I am writing a theory, for example, for any structure M, theory of M defined as all those sentences psi in SL such that M models psi is complete. Okay, if I am given a 4-element group Z mod 4Z, okay, then I will take every single sentence which is true in that structure. And well, the collection of all such sentences is a complete theory because it already made a decision. So what happens in this case is that, so psi, so theory of M models psi if and only if M models psi, right? So therefore, for every sentence, M will always make a decision. Yeah, a structure, a given sentence is either true in the structure or it is false. So a structure always makes decisions. So therefore, the theory of a structure is always complete. Now, just take a moment. We proved completeness theorem in the case of propositional logic. But I emphasized on the fact that that completeness theorem and soundness theorem, they were about the proof system, proof calculus. But there is also Gödel's incompleteness theorem. And that incompleteness doesn't have to do with a proof system, but it has to do with completeness, incompleteness of a theory. It's the same word, but totally different contexts. Okay, our last lecture will be about Gödel's incompleteness theorems. So there we'll talk about certain theories being incomplete. Now, just before we leave, is any of the theories here complete? Theory of directed graphs, is that complete? No, it's not. It's empty. Gamma is empty. So if I say that for every element there is an arrow from that node, how do I express something like that? So this is not complete, yeah? If I write that for all W1 there exists a W2 such that R W1 W2. Now this is a sentence, so let psi denote this sentence. Then psi is not decided by gamma digraphs. Yeah, then since for psi equal to this, gamma digraph doesn't entail psi and gamma digraph doesn't entail negation psi. How do we decide this, whether it entails or not? Well, there is a model, there is a directed graph for which psi is true. And there is a directed graph for which negation psi is true. So therefore, we cannot decide it. You understand? We'll continue talking about it in the next lecture. Yeah? And we'll talk more about models and theories.